Everybody. Today we have a seminar by Ron Levie, and Ron, he has received his PhD degree in applied mathematics from Tel Aviv University. He has done a postdoc at TU Berlin, and he now is a researcher in the Bavarian AI Chair for Mathematical Foundations of Artificial Intelligence at LMU Munich. His research interests are in the areas of applied harmonics analysis, mathematics of deep learning, graph neural networks, and explainability in deep learning. And today he's going to be talking to us about the transferability of spectral graph neural networks. So Ron, go ahead.
Thank you for the introduction. I'm very happy to be here today. So I'm going to talk about spectral graph convolution networks. So this is the class of methods of graph neural networks in which convolution is defined in the spectral way as multiplication in the frequency domain of the graph. And I'm going to prove that they have good generalization capabilities. So in this context, transferability means the ability to transfer a convolution network between different graphs. And the idea is that if we train on a certain set of graphs, we want to be able to show that the network is also meaningful on other graphs. Okay, so let's start with the basics. If you know what a standard convolution network is, then a graph convolution network is the same thing. The only difference is that signals are now defined over the nodes of graphs and not over the nodes of Euclidean grids. Okay, so a graph convolution network starts with a signal on the graph, applies convolution, activation, pooling, and so on. And because data is often graph structured, this is very useful and it has many practical applications. And by today, graph deep learning is it has a lot of impact on the industry. Okay, so suppose we have a multi-graph setting, a data set that consists of many different graphs and many different signals on these graphs. The network that we train should generalize to graphs that we haven't seen in the training set. So let me illustrate the ideas with this picture. So if we have two graphs that represent somehow different phenomena, then I want my network to have a different repercussion on both graphs. But if I have two graphs that somehow represent the same phenomenon, then I want my network to do approximately the same thing on both graphs. Because maybe during training, I'm going to see this graph, and during testing, I'm going to see these graphs. And this leads us to the notion of transferability in this context, which means a filter is called transferable if whenever two graphs represent the same phenomenon, the filter or the convolution network has approximately the same repercussion on both graphs. Okay, and the goal is to prove transferability of spectral graph networks. Now, because I want to prove something mathematical, I need to first of all formulate it mathematically. So what do I mean by graphs representing the same phenomenon? I need to model this. And I also need to model a network having the same repercussion on two graphs. And once I have these models, the goal is to prove transferability. So in this talk, I'm going to present three approaches to model these notions. And for each approach, we are going to have a corresponding theorem of transferability. Okay, so let's start again with the basics. If you want to generalize standard convolution networks and define graph convolution networks, you need to generalize three things. First of all, the activation function, right? But this is trivial because the activation function simply applies pointwise on the features. We also need to generalize pooling. So this is done via graph coarsening. There are different ways to do it. The idea is to take somehow nodes with strong connectivity and collapse them to a single node. And this is the way we downsample the graph. Okay, so there are different ways. Let's take it as a black box and let's focus on how to define convolution on graphs. So basically, there are two approaches for defining convolution on graphs. Both of them are inspired by the classical Euclidean convolution. Spatial approaches are inspired by the sliding window point of view of convolution. So here the goal is to define a rule for aggregating the feature information from the neighbors of each node and update accordingly the value of the node. And because this rule doesn't depend on the index of the node, we think about it as a sliding window, or more accurately, it is a translation equivariant. So we can think about it as a convolution. Now, the spectral approaches, these are inspired by the classical convolution theorem that says that convolution in the spatial domain is equivalent to multiplication in the frequency domain. So now, in order to define spectral convolution on graphs, we need to define the frequency domain of a graph. And once we have that, a filter or a convolution operator is defined as multiplication elementwise in the frequency domain. Okay. So you can find many papers from the last 4 years that claim the following thing. They say that spectral approaches are okay. You can use them if you have one fixed graph, but if the dataset consists of many different graphs, you shouldn't use spectral approaches, because anything that you learn on one graph is completely meaningless on another graph. This is what is claimed. And in fact, this is not true. It's not true in theory, which is what we prove, and it is also not true in practice. There are a few papers that also show that this is, in practice, spectral methods are transferable. Okay, so by today, it is already known to many people that spectral methods are transferable, but the unfortunate thing is that this past misconception led to a culture in which whenever somebody comes up with a new graph convolution approach, in a multi-graph setting, they only compare it against spatial approaches and almost never against spectral approaches. And we think this should be changed. Okay, so let's now see how to define convolution operators on graph in the spectral approach. So again, we take inspiration from the classical frequency domain, right? We want to define the frequency domain of a graph. So in the classical case, one way to derive the classical frequency space, the Fourier modes, is as the eigenbasis of the classical Laplacian on the interval. The classical Laplacian is the second derivative. And because we have notions of Laplacian also for graphs, we can do the same for graphs. So we take some graph Laplacian. This is a self-adjoint operator or a symmetric matrix operator that somehow encapsulates the geometry of the graph, or more accurately, the eigenvectors tell me how I can oscillate on the graph. There are different ways I can oscillate in the graph, and the eigenvalues are, in some sense, the frequencies. Okay, and now a convolution operator on the graph is defined as follows. Given a signal on the graph f, I'll compute the frequency coefficients of the signal as the inner product of the signal with the different Fourier modes. These are the eigenvectors of the Laplacian. Then each frequency coefficient is multiplied by a different frequency response, and we sum up against the frequency, the different frequencies. Okay, and choosing different filters is choosing different frequency responses, different CJs. Okay, so this definition, it's not just a definition, it is also an implementation. If somebody gives me a graph and a signal, I know exactly what to compute. But as an implementation, it has two major drawbacks. First of all, it is computationally demanding, because if somebody gives me a graph now, I need to first of all compute the eigendecomposition of the Laplacian, and this is inefficient. And even if the data set consists of just a few graphs and I can pre-compute the eigendecomposition of the Laplacian, I still need to compute all of these inner products explicitly, and I need to compute the sum explicitly, and this is inefficient because there is no general FFT algorithm for graphs. And the other drawback of this specific implementation is that it is not transferable. So let me explain why it is not transferable. So in transferability, I need to first of all define what I mean by two graphs representing the same phenomenon. And perhaps the most basic definition would be two graphs which are small perturbations of each other. Namely, I have a graph, and the second graph is maybe the second graph Laplacian is a small perturbation of the first graph Laplacian. So obviously, because these two graphs are almost the same graph, they represent the same phenomenon. Now, the problem is that eigendecomposition is not stable. If I take my graph Laplacian and perturb it a little bit, then the eigenvectors can change by much. And then the repercussion of the filter on the signal also changes by much. So I don't have transferability because I don't have stability. Okay, so, but luckily state-of-the-art spectral methods don't implement convolution operators. With this implementation, state-of-the-art methods are based on functional calculus implementation of convolution. So what is functional calculus? This is the theory of applying functions on operators. And in the special case of a self-adjoint operator with an eigendecomposition, so here lambda j are the eigenvalues and uj are the eigenvectors, the application of a function on T is by definition applying the function g on the eigenvalues and keeping the rest of the eigendecomposition as it is, keeping the eigenvectors as they are. And in some sense, this definition is the canonical definition, because in the special case where g is a polynomial, I can apply g on T in two different ways. First of all, I can use definition 1. And secondly, I can replace the powers in the polynomial by compositions of T on itself. And it turns out that we get exactly the same definition. And in this sense, this definition 1 is canonical. And it also works for rational functions, where for a rational function in the denominator, a rational function is a polynomial divided by a polynomial. So if we want to implement it directly in the graph domain, we also need to invert the polynomial. And again, we get exactly the same definition both ways. Okay, so how do we use functional calculus to define filters? We define filters as functions of the graph Laplacian. Okay, so let's compare this implementation to the naive implementation. Previously, the frequency responses were parameterized via the index of the frequency j, and now the frequency responses are parameterized via the value of the frequency lambda j. And this makes the whole difference because now we solved both of the problems that we had before. First of all, we solved the instability problem, because now if somebody gives me a graph and perturbs it a little bit, then yeah, the eigenvectors can change by much, but also lambda j changes and the frequency response g lambda j changes accordingly, and this compensates for the instability. Or more accurately, different lambda, if I have an eigenspace which is more than one-dimensional, the frequency response has to be fixed for this eigenspace. So I don't have a problem of non-uniqueness here. Okay, so basically what you can prove is that the error in the filter is bounded by some constant times the error in the Laplacian. So we have linear stability. Now the second problem that we solved is the computational problem. Because now if G is a polynomial, you don't ever have to compute the eigendecomposition of the Laplacian. This right-hand side only lives in theory, and in practice, you apply the polynomial on the Laplacian directly in the graph domain, using compositions of the Laplacian on itself instead of powers. And this also works for rational functions, where, as I said before, for a rational function, we invert for the denominator, and this can be approximated directly in the graph domain. And both of these methods, the computational complexity is linear in the number of edges in the graph. So they are efficient. Okay, so let's go back to the problem of transferability. We already discussed one approach to define transferability. This is the stability approach. So here, two graphs represent the same phenomenon if they are a small perturbation of each other. So namely, we have the same number of nodes, but the graph Laplacians are a small perturbation. So as two matrices, they are almost identical. and a network or a filter has similar repercussion on both graphs, this is easy to define because we have the same number of nodes. We can simply compute the norm error between the outputs of the filters. So now I want to focus on the second approach for defining transferability, the sampling approach. And then later I'm going to discuss shortly the Graphon approach to transferability. Okay, so let's start with the sampling approach and let's try and gain some intuition. So weighted graphs can be seen as points and strength of correspondence between pairs of points. And this resembles a little bit the notion of metric spaces, which are points and distances between pairs of points. So it is natural to think of graphs as discretizations of metric spaces, where when the distance in the metric space increases, the edge weight decreases. And this leads us to the basic assumption in this approach to transferability. Graphs that represent the same phenomenon are discretizations of the same metric space. Okay, so this definition makes complete sense in geometric settings. So think, for example, about meshes discretizing surfaces. Okay, so I can have the continuous sphere, which is the underlying phenomenon, and I can have two graphs representing or sampling this sphere. One can have 100 points and the second graph can have 1000 points. Both of these graphs represent the same phenomenon, so I want to be able to prove that a fixed convolution network has approximately the same repercussion on both graphs. Okay, so in geometric settings, it makes complete sense. And there is also a lot of evidence that networks like www or social networks and protein interaction networks also have some underlying latent geometric space from which they are sampled, typically hyperbolic space. So it also makes sense to consider these types of graphs. And you can also stretch the imagination and think about non-geometric settings. For example, a citation network. Okay, so a citation network is a graph in which each node represents a paper, and there is an edge between a pair of nodes if there is a citation between the papers. Now, if you want to adapt this basic assumption, you need to be able to imagine a limit space where the number of papers goes to infinity, and at the limit there is a continuum of papers, and you need to be able to somehow define a metric there where when the distance increases in the metric, then the probability of having a citation between papers decreases. And if you're willing to make this leap of faith and consider this setting, you can use our analysis. Now, in practice, you don't really need to know anything about this latent space. In practice, everything is applied directly on the graph, but we use the assumption of existence of this underlying continuous space for the analysis. Okay, so I wrote here that the underlying continuous space is a metric space, but I only wrote it here for intuition. And in practice, in the proofs, we don't ever need to use the metric assumption. It is enough to assume that the space is a Borel space, a topological space with measure. And for most of the results, it is even just enough to assume that the underlying space is a measure space. Okay, so now I know what I mean by two graphs representing the same phenomenon. They sample the same continuous space. I still need to define what I mean by a network or a filter having approximately the same repercussion on two graphs. Now, the problem is that there is no direct way to compare the two graphs because they have a different number of nodes. But both of them discretize the same underlying space. So in our approach, we treat transferability as follows. We start with a generic signal in the underlying continuous space, and we sample it to both graphs. And then we apply the filter to both graphs, right? So the filter G is the same, but it has it is represented differently in each graph. G of the first graph Laplacian and G of the second graph Laplacian. And now to compare the two outputs, we interpolate the result back to the continuous space. And now because both output signals live in the same space, I can compare them using some norm error, some L2 error. And what we do in our theory is prove that this error is small. Okay, so to develop this rigorously, we developed a digital signal processing framework in which analog domains are the underlying continuous spaces, Borel spaces, with operators that we call the continuous Laplacian. So the continuous Laplacian is a self-adjoint operator, and it describes the geometry of the underlying space. Namely, the eigenvectors describe the different ways you can oscillate in this space. Digital domains are graphs with corresponding graph Laplacians that describe their geometry. We consider Paley-Wiener spaces. These are the spaces of band-limited functions on the underlying continuous space. We define a sampling operator. So this is the operator that takes a signal defined over the graph and returns a signal defined over the the other way around. The sampling operator takes a signal defined over the underlying space and evaluates it at sample points to give a signal defined over the graph, right? So we think about the nodes of the graph as sample points from the underlying space, and we define interpolation operators. These are the operators that take signals defined over the graph and return signals defined over the underlying continuous space. Okay, so now we are able to prove the first result that we call the transferability inequality of filters. So let me explain what this inequality means. So basically, it means that the transferability error of the filter is bounded by the transferability error of the Laplacian plus the consistency error. So let me walk you through how to interpret this inequality. So P is the projection to the Paley-Wiener space, which is generic. We can take any Paley-Wiener space. So for intuition, let's disregard for a second this projection. So here in the left-hand side, we start with a generic signal in the continuous space. We sample it to the graph. We apply the graph version of the filter, and we interpolate the result back to the continuous space. On the other hand, we start with the continuous filter, with the continuous signal, and immediately we apply the continuous version of the filter, G applied on the continuous Laplacian. So this describes the transferability error between the continuous filter and the discrete filter. In the right-hand side, here we start with a signal in the continuous space. We sample it and apply the discrete Laplacian. On the other hand, we take the continuous signal, apply the continuous Laplacian, and then sample it. And this describes the transferability error of the Laplacian. And the last term is the transferability error of sampling interpolation. So we call it the consistency error. If we start with the continuous signal, we sample it, and immediately after interpolate it, this entails some error. Okay, so there are different versions of this inequality. I put here a couple of them. And it is interesting to note that we don't really, for this theorem, we don't really need the digital signal processing framework. The theorem is very generic. It doesn't really matter that S evaluates a signal at sample points. S can be any linear operator, and R can be any linear operator. It doesn't even matter that G is a graph. This inequality is very general, and we can use it. We can use this inequality in additional use cases. For example, we can think about the underlying space as a graph itself. So it's a fine version of a graph, and G is a coarsened version of the graph. For example, using the Gracchus algorithm, or some other graph pooling approach, and S is the pooling operator. So in this case, we can prove a transferability inequality under pooling. Basically, the application of the filter on the fine version of the graph is approximately the same as the application of the filter on the coarse version of the graph. And we can also use this theorem to prove a stability inequality, where both M and G are the same graph up to a small perturbation. Okay, so we can take this transferability inequality, which is for filters, and apply this theorem layer by layer on an end-to-end convolution network and prove the transferability inequality for convolution networks. Okay, so as before, the transferability error of the convolution network is linearly stable in the transferability errors of the Laplacian and in the consistency error. Okay, so up until now, what we showed is that if the transferability of the Laplacian is small and the consistency errors is small, then the filter or the convolution network is transferable. But who guarantees that the right-hand side here is small, right? The question is it reasonable to assume that graph Laplacian are transferable? Now, obviously, here I cannot give you a universal mathematical proof, because it's very easy to construct an adversarial example in which, for example, I can take a data set of surfaces and deliberately sample them badly. So Laplacians are not transferable, right? I can take the bunny and only sample 1 million points just on the ear, right? So obviously, I cannot guarantee that the right-hand side is always small. It depends on the data generation process, but we still want to prove something under reasonable assumption, and we prove the following thing. So if graphs are constructed by sampling random points from the underlying space, then we can show that graph Laplacians are transferable in high probability, and therefore convolution networks and filters are also transferable in high probability. Okay, so under this modeling assumption of how data is generated, we have transferability. Okay, now I want to talk about the second approach to transferability. This is the Graphon approach. So let me start with a reminder on Graphon analysis. If you don't have experience in Graphon analysis, I'm going to try and explain everything intuitively. Hopefully you'll be able to follow, but it's not, don't even try to read the formulas. They're not very simple to follow. So a graphon is a limit object of graphs, and in some sense, a graphon is a graph with a continuous index set of the nodes. So the node index set is a standard probability space. You can think, for example, about the unit interval. And then a graphon, you can think about it as a continuous version of the adjacency matrix. It is a mapping that takes a pair of indices in the continuous index set and returns the weight of the edge between them. And you can also think about the graphon as the continuous version of the graph shift operator. Okay, so how do we define convergence in the graphon sense? We define it in homomorphism density sense. So let me try and explain the intuition behind this definition. We consider simple substructures of graphs, namely simple graphs. So for example, and we call them motifs. For example, F can be a triangle or a cycle, any simple graph. And then we count the number of times that we see these simple graphs in our graph G. Okay, for example, if F is a triangle, we count the number of times or the number of triangles in the graph G. We don't, okay, so, and we also normalize, so it's not really counting the number of times we see triangles in G, we compute the density of triangles in G. So this is called the homomorphism density of F in G. And we can also count the number of times we see the motif F in the graphon. So the Graphon is a continuous entity, so we don't really count, but we can, in some sense, integrate the number of times we see the motif in the Graphon. And then the sequence of graphs Gn converges to the Graphon G by definition if for every simple graph F, the homomorphism density of F in the graphs converge to the homomorphism density of F in the Graphon. So basically in this approach, two graphs are close to each other if they have the same or approximately the same substructures. Okay, now there is a way to take a graph and induce a Graphon from it, and to take a signal and induce a Graphon signal on it. The idea is to take the continuous index set, P, and partition it to subsets. For example, if P is the unit interval, I can partition to small interval, non-intersecting interval. And then you take the graph adjacency matrix and extend it as a piecewise constant function over the continuous index set. And we can do the same thing. Okay, so we get a Graphon this way. And we can do the same thing for signals. We take the discrete signal and extend it as a piecewise constant function over the continuous index set, and we get a signal defined over the continuous set of indices of the Graphon. Okay, so now we are ready to go back to the paradigm of how to approach transferability. So we need to define what we mean by two graphs representing the same phenomenon, and we need to define what we mean by a filter having approximately the same repercussion on two graphs. So in the Graphon approach, two graphs with Laplacian delta and delta prime represent the same phenomenon if for every simple graph or every motif, the homomorphism density in the first graph is approximately the same as the homomorphism density in the second graph. Okay, so as I said before, two graphs represent the same phenomenon if they have the same substructures. Now, we say that a filter has approximately the same repercussion on the two graphs if the following holds. So we take the filter, we apply it on the first graph Laplacian, we apply it on the second graph Laplacian. Now I cannot compare them yet because the two graphs can have a different number of nodes, but then I induce a Graphon from the two filters. And if these two Graphons are approximately the same, we say that the filter represents approximately the same, has approximately the same repercussion on both graphs. Now here, everything is up to permutation because there is no natural way to index the nodes of a graph. Okay, so up to permutation, this approximation is true. Okay, so now we are ready to present the first theorem on transferability of filters in the Graphon sense. If we have a sequence of graphs that converge to a Graphon in the homomorphism density sense, and the only thing we need to assume on the filter is that it is continuous and that the filter is 0 at 0. Now, this is very easy to enforce in practice because, for example, if the filter is a polynomial, simply ignore the constant part of the filter. So under this assumption, up to a permutation, if I take my filter, apply it on the graph Laplacian and induce a Graphon from it, this converges in operator norm to the filter applied on the Graphon. Okay, so here G of W is in the functional calculus sense, right? It's not a composition of a function on a function. We think of W as a kernel operator. So W is the continuous shift operator. It's like a continuous version of a matrix multiplication. Okay, so this theorem, you are going to put it in archive very soon. It is not yet published. We also have other versions of the transferability theorem in which the transferability of the filter is is treated non-asymptotically. So we have a transferability inequality, and we can also use this theorem on an end-to-end convolution network to derive a transferability result for convolution networks. Now, the first theorem that treated the Graphon approach was by Ruiz and Ribeiro in 2020, but in their theorem, they restricted the analysis only to polynomials. And we prove for any continuous function, which is more general. And we use the mathematical tool that we use is functional calculus. So for example, now it applies also to rational functions. Okay, so to ARMA filters and Cayley nets, for example. Okay, so let's take a step back now and think again about the problem of transferability. Graph convolution networks can manage transferability in different ways, and we roughly categorize them in two approaches. We have concept-based transferability. So here the idea is that if the network sees a multigraph setting, if the data set has many graphs, then the network learns concepts that promote transferability. So basically, because the network sees many graphs during training, it learns to cope with a variety of graphs. Now, on the other end of the spectrum, we have principal transferability, and this is what we proved in theory. This is the built-in capability of graph convolution networks to transfer between graphs, and it doesn't depend on a specific choice of the filters, and it doesn't depend on training. And we believe that in practice, spectral graph convolution networks achieve good results in multigraph settings due to both of these types of transferability. But it is interesting to ask whether it is possible to somehow isolate principal transferability from concept-based transferability and test in practice, in experiments, if we indeed have principal transferability. And in fact, this is not difficult to do because we can take a network and train it on one fixed graph with a fixed resolution, so it doesn't have an opportunity to learn concepts that promote transferability. And then we test it on the graph with different resolutions. Okay, so in this toy example, we took in blue a spectral approach and in red a spatial approach, and we compared the accuracy when you change the resolution, and we see that the spectral approach has competitive transferability capabilities. Now, of course, this is just one example. I'm not trying to say that spectral methods are more transferable than spatial methods. Okay, so we have additional examples, but let me skip them because maybe more interestingly, 6 months ago, Xavier Bresson and his PhD student published a paper in which they said the following thing. So these people are saying that graph spectral methods are transferable, but all of these other papers claim they are not, and nobody tried to put it to the test until now. Actually, there were a couple of papers that did, but not very extensively. So their goal was to try and prove our theoretical results with experiments. So they took ChebNet, which is a spectral graph convolution network based on polynomials from 2016, and tested it in a set of multigraph benchmarks. And they compared the results to top of the chart spatial methods. So they took vanilla methods. Of course, they optimized the hyperparameters, but they didn't add special augmentations tailored specifically to the specific problem, right? So they only compared against vanilla methods, and they saw that ChebNet reaches state-of-the-art results in most of the benchmarks, if not in all of them. So these are the results from their paper, and maybe interestingly, it is interesting to note the first experiment. You can see a very big a gap here in the accuracy between ChebNet and the next spatial method. And this data set is synthetically generated by sampling some underlying continuous phenomenon. So this really validates, it really corresponds well to our theory and validates the theoretical results. Okay, so in conclusion, I showed you today a paradigm of how to treat transferability of graph convolution networks, where you need to define mathematically what it means for graphs to model the same phenomenon, and you need to define mathematically what it means for a network to have approximately the same repercussion on graphs. And once you have these models, you can derive transferability inequalities. So I showed you three approaches: the stability, the sampling, and the Graphon approach. In the sampling approach, if graph in the sampling approach, graph spectral filters and convolution networks are transferable if Laplacians are. Is it reasonable to assume that Laplacians are transferable? Yes. If graphs are randomly sampled from Borel spaces, then graph Laplacians are transferable, and then convolution networks are transferable. So we proved transferability in practice, and there are also papers that show it. We proved it in theory, and there are papers that show it in practice. And there is also this experimental study, which is more extensive. So in conclusion, if your data consists of many different graphs, then you shouldn't exclude spectral approaches because they are transferable both in practice and in theory, and you may obtain state-of-the-art results if you use a spectral approach. Okay, so basically this is what I wanted to talk about, and thank you for the attention.
Thank you to you, Ron. Very, very nice.
Okay, so yeah. I would say that if you want, Ron, we can take questions from the public.
Yeah.
So if anybody has questions, feel free to go ahead and ask.
I have one question.
Mm-hmm.
It's coming from the section where you were talking about computing the similarity between graphs by projecting into the continuous space and then basically measuring the norm. There was a figure of like two balls connected by a, yeah, this one.
Yeah.
So my question is, okay, first of all, so this is a graph that we are assuming comes already with spatial coordinates. So
No.
I don't just get the adjacency matrix, but I also get coordinates of the points, or what?
No. So the way you do graph convolution networks is the classical way. We don't change the computational machinery, right? How do you apply a filter on the graph Laplacian? You don't need to know anything about the latent underlying space. If G is a polynomial, you just need to take the adjacency matrix and compose it on itself. Now, and there is no information about the embedding in the underlying space. The assumption that there is some underlying space is only used for the theoretical analysis, right? It is used so we can define what we mean by a filter having approximately the same repercussion and to be able to prove inequalities. But in practice, when you work with convolution networks, you don't need to know anything about this underlying space. Okay.
Okay, thank you.
Any more questions?
I have a one, Ron. What about some partial transferability? Let me elaborate on this. So you have the two globes that are connected, and you have another graph which has only one globe. The other one is missing, or the phenomenon is only a partial view over the phenomenon, and so on. Can you elaborate? Can you comment this?
Yeah, so maybe I'll say two things about it. So the first thing is you can take this, as I said in the talk, you can take the, you can take the transferability inequality, which is very generic. You don't need to know anything about graphs here, and you can treat you can add a third term in which you have a perturbation also of the underlying space. Okay, so this is the one thing that you can do, is that you don't need to assume that the two graphs sample exactly the same space, but the same space up to small perturbation. Now, your question was not a small perturbation, but somehow partial information.
Yes,
right?
correct.
You have only one part of the graph. Now, the analysis that we do here is L2 analysis, and in some sense, it is the worst case analysis. In some sense, it integrates the error over the whole domain. So this analysis is not going to work, and you would need a pointwise analysis if you want to consider cases where somehow there is some area which is of interest to you, and this area is sampled well, but away from this area, maybe the graph is not sampled well. So there is currently we don't have an analysis for that, but in fact this is something in our pipeline, and we are working on a pointwise theory, because this is actually important for robustness of graph convolution networks.
Right, absolutely. And I have another question. Thinking of space and time brings me back to the Gabor transfer or wavelets, things like that. Would that make sense to do something similar here, where we have frequency and time?
Yeah, definitely, and there are papers that do that. They define the wavelet transform in the spectral sense on graphs. So basically, in the wavelet transform, you can think about the wavelet transform as the choice of these filters. Right, you have these filters G applied on the Laplacian. So the G's that you choose are different filters which extract different scales. So there are, I don't remember right now the titles, but I think there are a couple of papers on that.
Okay, thanks a lot.
You're welcome.
So I had a question about the fact that you are able to relate your results also to the case of pooling. And I was wondering if, like, from what you said before, so the sampling operation is affecting the consistency error. I think you mentioned, you called it like that. And so my question would be, can we use these results to maybe say something about the desired form of this subsampling operator for the graph, right? So can we optimize S so that we get a particularly well-formed course in the graph?
Okay, so if you want to somehow use the transferability inequality to design a pooling method, or maybe to learn a pooling method, one thing would be to try and minimize the right-hand side. Because if the right-hand side, the smaller the right-hand side is, the smaller the left-hand side is. So you would need to train, so S here is the pooling operator. You would need to learn a pooling operator that minimizes the error between starting with, so this error is if you start with a signal on the fine graph, you do pooling and apply the coarse version of the Laplacian. On the other hand, you take the signal and compute the fine version of the Laplacian and then do pooling. You want to minimize this error. And this can promote transferability.
Thank you.
You're welcome.
Hi, may I ask a question? Yeah, well, first of all, thanks for the presentation. It was pretty clear, although the concepts are not so straightforward. I wanted to ask you how much is all this theoretical development specific to the Laplacian operator, and if it is possible to either extend or just have a small derivation for possibly other operators. And the second question was related to the fact that you said at a certain point that you need a sort of limited band for your spectrum. I wasn't No, I couldn't understand really what you meant by that.
You mean the band limited spaces?
Yeah, exactly. Is that referred to the filter? So G as finite or compact support, or?
Okay, so let me explain. So the first question was about the graph Laplacian. So the theory doesn't depend on any construction of the Laplacian. You can take any shift operator. Basically, you can take any self-adjoint operator you like. You only need to assume that the operator is, it doesn't even have to be a bounded operator. You only need to assume that it has a discrete spectrum. Because in general, unbounded operators can have, they don't have to necessarily have an eigendecomposition. So you need an eigendecomposition for this theorem. It is potentially possible to extend it to operators with a continuous spectrum. I mean, it is possible to do it. Now, for the second question, it was a general question about the importance of the Paley-Wiener spaces. So this is something general about signal processing. When you do classical signal processing, the Nyquist-Shannon approach, what you do is there is no way to extract, to recover the signal if it has high frequencies, right? So somehow sampling has to correspond somehow to the band that you work with. Now the band in this inequality is generic. You can choose lambda as you wish. So in some sense, this is a set of theorems. For each band you have a different theorem. Now, if you choose a very small band, then the right-hand side is going to be small, but the theorem is less meaningful. It only means that the very smooth part of the signal is transferable. And if you use a large lambda, then the theorem says that also in some sense, the less smooth part of the signal is transferable, but then the right-hand side is larger. So you have here a freedom in how you want to approach the problem, what Paley-Wiener space you want to study. And basically, always the very high frequencies, the information in the very high frequencies is going to be lost. Does this answer your question?
Yeah. Thanks. So in this sense, so it's more related to the signal than the actual space or the topology of the graphs or the underlying space.
Yeah, these are the Paley-Wiener spaces of the underlying continuous space, not of the graph. So these are the band-limited signals on the continuous space.
Okay. Thanks.
Yeah. So do we have additional questions? If you have a question, go ahead and ask, because I don't really see the audience. I never used this app before.
Yeah, no, I don't think we have. I don't think we have any raised hands. So I think we can wrap it up. So thank you very much, Ron, for being with us. It was an amazing presentation, and
absolutely.
So thank you for being with us.
Thank you for having me.
Absolutely, it was really an enjoyable seminar. Thank you so much, and also all the others, I think that they enjoyed that. Thank you, and let's keep in touch.
Yeah, sure.
Bye. Ciao.
Bye.
Nice evening.
Bye.
Thank you. Bye.